Video we will use SERIESSUM and LINEST for regression of geometric series. Here we have a geometric series of y equals 1 over 1 minus x. And the series expansion will be 1 plus x squared plus x cubed plus x to the fourth to infinity. We will use, we will generate a data set for this. This is good only if the value of x is between negative 1 and 1. So we'll use the range negative zero point 0.9 to positive zero point 0.9. Let's generate the data set for the 1 over 1 minus x. So array formula 1 over 1 minus the x values. Next, we generated the formula, the expansion. You will notice the coefficients are all 1 for each term. So we enter the coefficients of 1. And now we use the series sum. You will also notice that the power of is incremented by 1, starting from x to the 0, which is 1, to x to the 1, which is x squared, where the power now is 2, so it's incremented by 1 to infinity. So we have our formula, series sum of the x values, that's between negative 1 and 1, and our starting power will be 0, incremented by 1, and the coefficients all will be 1. And we generate the chart. Insert chart, scatter chart. So that's the expansion. We also add the geometric series itself. So this is now the geometric series. You will notice the red, which is the original, is the same as the expansion until the values of 0.75, positive 0.75. Beyond positive 0.75, they vary a bit. That shows here in the lower portion. So there is now a difference after 0.75. So we will regress this because it is easy to linearize the original formula. So we regress it using the reciprocal, which is RA formula 1 over this value. Because to regress it, you need to have 1 over y, and it's 1 minus x. That is in the form of 1 over y equals b0 plus b1x. And you factor out the 1 comma x and b0 b semicolon b1. b1 comma x is what we're going to solve next. So we have the 1 column and the x column, which is array formula of the x values. Now that we have this column, we can use the LINEST. The LINEST will be data y, the linearized data y, and data x. And we show the full statistics. It's perfect. Our b0 is perfect 1, and b1 is perfect negative 1. That's because we are regressing the original, or regressing it by itself. So we are regressing the original range data set by itself. That's why we have a perfect value of 1 and negative 1. And our standard error values is 0. And R square is perfect 100. And the residual sum whole square is also perfect 0, or almost 0. Then a negative, very small, negative 30. Now we can regress the expansion. To regress the expansion, we replace this with the expansion. Instead of the original, we now use the expansion. So array formula of the expansion, that's 1 over y. Now we don't have a perfect 1, but almost 0.98. And we don't have a perfect negative 1, which is negative 0.95. Our standard error is still very small, 0.02 and 0.01. Our R square is 99.2%. That's almost perfect. Our residual sum of square is zero, almost zero, 0.03. Very small. So this completes the use of series sum and LINEST for the regression of geometric